Hello and good day, everyone. My name is CrysAlisᴾṕ and I am an application scientist here at Rigaku Europe SE, stationed in Neu-Isenburg in Germany. This lecture is concerned with the collection of powder diffraction data on a single crystal instrument using only micrograms of powder. So what's the motivation behind this? Well, basically we had a look on the survey that some of you did in preparation of this crystallography school, and we just had a look at the top results, and the top results were molecular structure and chemical properties and powder diffraction. And yes, we thought, well, we can do it. We can do both basically with our instruments. And so today we are going to focus on powder diffraction with a single crystal instrument. Why and when should you use your single crystal diffractometer for powder diffraction? Sometimes single crystals are simply not available from your synthesis, or you already know the structure and you want to control your synthesis outcome without performing a sometimes time-consuming crystallization. Under these circumstances, you want to perform a powder diffraction experiment. Powder diffraction is also a great tool for analyzing the composition of a bulk sample or just a mixture of different compounds. You might also not have access to a powder diffractometer, or you only have a tiny amount of sample at hand. So while for most powder diffractometers at least milligrams of sample are required, only micrograms are needed for a single crystal diffractometer. Most single crystal instruments are already equipped with a temperature control device, like for example an Oxford CryoStream, while most powder instruments do not have this option. That comes in very handy, as you can easily employ these devices for temperature experiments. Furthermore, we can analyze even materials like fibers or polymers by performing a stress analysis or a pull figure measurement on a single crystal instrument, while powder instruments often need special attachments in order to do so. Furthermore, single crystal devices are regularly equipped with molybdenum or silver radiation sources, and these are very rare to find for, well, not absolutely dedicated powder diffractometers. Usually powder diffraction is performed with copper radiation, always. And if you want to do a PDF analysis, you probably would like to use silver or molybdenum radiation. You don't have it on your powder instrument, so you can employ your single crystal instrument for that. But today we will focus on the collection of powder data for qualitative and quantitative analysis, and we will start with the sample preparation. Most sample preparation will be performed under the microscope, which will be present in most single crystal laboratories. Here we can get a good estimation of the crystallite size. If the powder looks like the one on the left hand side here, you should definitely perform single crystal experiments with these crystallites. But if you still want to perform a powder experiment, they are way too big. For a powder, you would aim for a homogeneous crystallites in the single micrometer range. You can achieve this by grinding your sample or squashing it with another microscopic slide or a spatula. Next, you want to mount your sample. For an almost background-free data collection, you can mount quartz glass capillaries or Kapton tubing. Both come in various sizes and can be sealed airtight in order to protect the sample. You can mount them in a standard sample holder, like here, or on a magnetic mount, like this. For an excellent instruction on how to load quartz glass capillaries, please visit the YouTube channel of the Argonne National Laboratory, Beamline 11BM. Way quicker is the mounting on any medium-sized single crystal mount, like a nylon loop or a mitogen or a fiberglass. You apply a little bit of oil to the mount and then dip it into your powder sample. You should not use too much oil, as this leads to a higher background, and the final powder sample should not vastly exceed your beam size. So samples of 100 to 200 microns are fine, like this one. If you want to use the mounting on the loop technique, it is recommended to deactivate your CryoStream completely. Otherwise, your sample might get blown away. You can do so by shutting down your CryoStream and to also disconnect the dry air inlet for the dry air shield, like in this example here for the CryoStreamer 800. The exact setup of your crystal cooling device might differ. If you use long capillaries, it might also be necessary to retract the temperature device in order to avoid collisions. So next we would mount the sample and start an experiment. Therefore, let me switch the screen and start CrysAlisᴾṕ. If you are using a Rigaku instrument, your instrument control software is probably CrysAlisᴾٓ. However, for most instrument control softwares, you will have some kind of powder plugin. For CrysAlisᴾٓ, you can start the powder experiment by clicking this powder diffraction button here on the left-hand side. And with this dialog, you can just select your type of experiment. You can select the name, do a video snapshot of your sample. There are some options, but we don't need to address them now. And then you can set up an experiment. And there are a couple of different experiment types that you can choose of. With a phi scan, you can rotate your sample around phi during the experiment, and this will lead to additional randomization of the sample orientation. And this will ultimately improve your data quality. You can do this faster with a fast phi movement, as the title says. Then a Gandolfi move is a special movement that employs the omega and the phi rotation at the same time. And with the Gandolfi move for a single crystal, you can even perform this measurement at different kappa settings, leading to additional randomization of the sample. Furthermore, there are experiment types for isotropic stress measurement or a pull figure measurement. Next, you will have to choose a detector distance. Usually for powder diffraction experiments, you want to choose a rather large detector distance of about 10 centimeters, so 120 millimeters in this case will give us good data. Then you would like to choose a resolution range, and this is highly dependent on your sample. So for let's say organic substance, you would choose a 2 theta range up to 50 degrees only. Then there are a couple of other options for the experiment, which we do not need to address right now. Of course, we need to set an exposure time. You can select to either use one exposure time for the whole experiment or different exposure times for the low and higher angles, or for the range of detector position that you need to measure it. And with that, there are options for employing the high temperature or cry device in order to do temperature experiments. However, we choose not to do this at the moment. And with that, I would be done with setting up this measurement. This would lead to a measurement time of 3 minutes. And I could now just start it by pressing Start with Analysis. And with that, I would like to return to my slides. You will not need impeccable data quality in most cases. For a quick control of your synthesis, a 1-minute data collection with the crude powder will be sufficient. But sometimes you will need good data, and there are several ways to achieve these. If your diffraction images look like the one on the right hand side here, it has symptoms of an inhomogeneous sample with larger crystallites featuring these discrete diffraction spots. These lead to a broadening of the Debye Scherer rings and erroneous intensities. This can be treated by grinding the sample powder or by randomizing the sample orientation during the experiment with Gandolfi scans. If you observe very high background, you should reduce the amount of oil or sample holder in the beam, or you can switch to a Kapton tube or a quartz glass capillary. If your sample is strongly absorbing on your copper source or very weakly diffracting on your molybdenum source, it might be worthwhile to change the radiation type. In order to prevent overlap of the powder rings, you can move the detector to a long distance beyond the 10 centimeters, or you can employ the divergence control of your system, or if you do not have this, you can use very thin collimators. The dynamic divergence control is a unique feature of Rigaku single crystal diffractometers and comes in very handy for the collection of powder data. Employing the divergence slit is just as beneficial for powder data collections as it can be for single crystal measurements. It will improve the resolution of your powder diffraction data, and here you can see the improved resolution achieved after employing the slits. The improved resolution leads to observation of additional peaks, and you can see this especially nicely here in the green box. So I reduced the divergence from 10 milliradians to about 3 milliradians, and we can see additional peaks and way slimmer peaks as well. Similar effects can be achieved with very small collimators if you have these available. After the data collection, I want to quickly address the possibilities of powder data analysis. And, as a first step, I want to go back to CrysAlisᴾṕ. And this is an actual powder data set collected with the Synergy S, copper radiation. This complete data set consists of basically 2 frames. It was collected with 60 seconds exposure per frame, which led to about 2 minutes of data collection time. Now I can process these data by clicking again the powder experiment tool in the offline version of CrysAlisᴾṕ, and here I get the extracted powder pattern. There are some options for the powder pattern extraction. I can select a range of 2 theta limits, a 2 theta range that should be extracted. I can select a range of formats for the powder data, and I can select an additional scale factor. Press OK. Press Reprocess in order to extract the pattern. Now I can also perform an initial qualitative analysis, and this is done by loading the structure factors from the structure which we already know or which we anticipate to be in the powder, and I load it to CrysAlisᴾṕ. From this structure factors, intensities are calculated and we can compare them to our observed intensities. And as we can see here, the position of the peaks is in the right, is correct, and also the intensity correlates very well with the expected intensity of this powder. So as I just showed you, the qualitative analysis of your powder diffraction pattern is absolutely possible in CrysAlisᴾপ্ৰভ or probably also in your instrument control software. This example which I just showed you was from naproxen, which is an anti-inflammatory drug. However, for further analysis of powder data, you would like to swap to a true powder analysis software. There are a couple of different analysis softwares around. The solution from Rigaku is Smartlab Studio 2, which I would like to show you now. So this is Smartlab Studio 2. I already loaded some data from a single crystal instrument, a Synergy S device, for the analysis in the software. And well, while we can do qualitative analysis in CrysAlisᴾṕ, we can also do it better in the dedicated Powder software, of course. And the first thing I would like to do is to do a phase identification with a database search. And therefore I press the search match button here. And this opens the search match algorithm. I selected the PDF4+ database and I select the pharmaceutical subset because this again is a mixture of naproxen and another drug. So the first phase that was identified was naproxen. As you can see here, I double click it in order to retrieve the card information. I close it again and select it to be added to our candidate phase list. Then I repeat the search match. And the second result of the search match is flufenamic acid, which is the second phase in this two-phase mixture. I select the two crystalline phases to be added to our sample, and now all the peaks are nicely described by the phases that have been selected. As a next step, I would like to do something called Rietveld refinement or whole powder pattern fitting. In the Rietveld refinement, we refine our structural parameter to the observed data in order to improve the fit. So on the top we see an overlay of the observed data, the two phases, and on the bottom we see the residual. And as a first step, I would like to select the scaling factors in this table up here for both phases to be refined. And I select refine. This will lead to a drop of the R value and an improved fit. So as a first step, I would select the main phase. And for determining the main phase, I go to the summary here and have a look. The main phase is flufenamic acid with about 70%. And now I select the lattice and profile parameter of the flufenamic phase to be refined. I again select refine. This again leads to a drop of the R value and an improved fit. And I repeat the same step with the naproxen phase. So again, I select these sets of parameters to be refined. I select refine, and this leads to an improvement in the fit. And last but not least, I select all parameter to be refined, which results in our ultimate refinement. So as you can see, the residuals are pretty low, and this would be the result of a, let's say, crude refinement without touching the structure. So as you might notice, we could select to refine the structure, but I choose not to do because this is probably not the correct data for structure refinement. Also, the structure is known from a single crystal experiment, so we shouldn't change it. As a summary, we can see the result of this refinement. So we have about 27% naproxen and about 73% flufenamic acid in this sample. And this is basically the the result of this Rietveld refinement. So Rietveld refinement can be very easy. And you can do it also with your data, with the data from your single crystal instrument. So coming back from the Rietveld refinement to the phase identification, I want to show you another type of quantification approach, another type of quantitative analysis. And this is not by fitting the whole powder pattern, the whole diffraction pattern by fitting the structure model or the unit cell lattice, the lattice parameters and the peak shape, but by the integrated intensities of the peaks. I therefore go to a slightly different software part. Details are not of interest. So this type of quantification is the so-called reference intensity ratio quantification, and it works via the intensity, the integrated intensity of selected peaks, and the amount of phases is determined by reference intensities that have been measured experimentally for this phase and for a corundum standard sample in a mixture of 50-50%. So the details are not of great interest. However, this is a type of quantification that you can employ for almost any powder sample, where you just measure it and integrate in the intensity of selected peaks. You don't need to measure the whole resolution range. You could only measure this small little range and determine the intensity of these two peaks, and you reference them, and starting from these you can determine you can estimate the ratio between these two phases. So in this example, naproxen about 37% and flufenamic acid about 63%. So as you can see, these results differ quite a lot from the results of the Rietveld refinement quantification, and Rietveld refinement quantification is usually distinctly more accurate. And with that, I return to my slides. So you can do a quantitative analysis in Smartlab Studio 2 or another powder software with the powder data you got from your single crystal instrument, which is, I think, very interesting. The data quality is absolutely fine and absolutely sufficient for this kind of analysis. However, a Rietveld refinement, or whole powder pattern fitting, as we call it sometimes, is only one of many types of analysis that can be performed with powder data. However, it is, I think, the most common type of application that you will encounter. One of the more demanding types of application you can do with powder data is the structure solution from powder. It is absolutely possible to collect high-quality powder data that are suitable for structure solution and Rietveld refinement. We performed, for example, this experiment of this metal organic framework on the right-hand side with a wide 2 theta range and at a long detector distance and with a very low divergence. And we ended up with a data quality that is very similar to powder diffraction data from an actual powder instrument. And these data were sufficient for structure solution. But you can do more. You can employ your plate screener for screening multiple powders. You just take one of these crystallization plates that are usually employed for crystallization of protein samples, and you fill up the wells with powder. and then you can do a screening using your plate screener and your single crystal instrument. And I prepared this nice little video for you, where you can observe that each of the wells is measured in multiple runs. I selected a measurement time of 5 minutes for each well, with measurement with frame time of 1 minute each. And after a measurement is done, the robot automatically drives to the next well. You can observe that the sample is rotating during the measurement for improved sample randomization. And you can already expect from this frame that the data quality is not that bad. You can see a little bit of background which is added at low angles from the well plate. However, data quality is fine and absolutely sufficient for fingerprinting and for the determination of the included phases. And you can load a well plate with up to 96 positions or so and screen all the powders in an automatic fashion in one go. The pair distribution function analysis is one of the more demanding applications that you can do with powder data from your single crystal instrument. What is pairwise distribution function? A PDF is essentially a weighted histogram of atom-atom pair distances that exist within your sample or material model. Although a PDF is related to an autocorrelation Patterson function of the atomic structure, the derivation and concept derives from the total diffraction theory. A PDF analysis consists of 3 basic steps. As a first step, you would perform a total scattering measurement over a large resolution range, so up to high angles of about 160 degrees in this example. And you would perform this experiment using harder radiation, like as you do usually. So PDF experiments are mostly performed with molybdenum or silver radiation or even synchrotron hard radiation. Then this data is treated with a series of correction functions. And the objective of these correction functions is to get rid of all of the experimental and instrumental aspects of the data. And you will end up with the S over Q function, which is basically a function of the intensity. This function is then Fourier transformed to get the G over R function. And this is the histogram of the interatomic or intermolecular distances. Why would I want to use PDF analysis? The total diffraction and the related PDF analysis can be used to solve many of the same materials problems that are currently solved through Bragg methods. So for example, single crystal structure determination and powder Rietveld refinement. However, the real unity of the PDF approach is that it can be used to solve materials problems that cannot be addressed by Bragg-based methods. By PDF analysis, we can determine the structure from amorphous materials. We can also get the structure from nanophase polycrystalline or non-crystalline materials. And we can get supramolecular and or incommensurate structure beyond the unit cell. How can we do it? How can I collect and process data for PDF analysis? To some extent, the experiments are very similar to powder experiments, to usual powder experiments. We use the same mounting and randomization scans, and we use longer exposure times for high angle frames. However, to some extent, PDF analysis are different. Instead of kappa radiation, which is the standard for usual powder experiments, for Rietveld analysis and such, we use harder radiation, so molybdenum or silver. This gives us a higher Q range to access, and results in improved accuracy for low radii. Furthermore, it is absolutely essential to also measure the empty sample holder with the same strategy in order to get a good background correction. Furthermore, we always measure to high angles in order to cover a good Q range. The energy resolution is given here, and as you can see here in these plots, the resolution for kappa radiation in the low R area is not that good. The peaks are pretty broad, therefore the interatomic distances cannot be termed accurately. When it comes to the evaluation of PDF results, we have a choice of programs. We can do the data reduction in Smartlab Studio 2 and PDF-Get X3 or in AutoPDF by Simon Bates. And then depending on the evaluation type, we can choose to go to PDF GUI for a small box or local structure refinement, or RMC profile for a large box refinement. And I would like to conclude with a quick example of a PDF analysis. In this example, we mounted a few micrograms of nickel powder on a Kapton loop and performed a relatively quick experiment using the molybdenum source of a dual source copper moly synergy as dual flex. And with this, we got excellent data over the full resolution range of 160 degrees up to a resolution of 0.37 angstroms. These data were then processed in CrysAlisᴾṕ, so the powder pattern got extracted, and then further analyzed in AutoPDF. After that, the structure model was refined in PDXL, resulting in this G/R fit, which gives us the observed and the calculated G/R, observed one in blue, calculated in red, and the difference plot here on the bottom, which is well, extremely low. And this means the fit is extremely well. And nickel powder is kind of a standard for this kind of application. And this is a nice proof of principle that we can do it, and we can do it well. And with that, I would like to do a quick summary of this lecture. So I gave you an introduction to the sample preparation of powder samples for your single crystal diffractometer. You can mount samples either on a single crystal loop or in a capillary. Then you can set up a measurement either in CrysAlisᴾŻ or in your instrument control software. I showed you how you can process the data and extract the powder pattern. Then I showed you a type of qualitative analysis. So you could do qualitative analysis in CrysAlisᴾjourd in your instrument control software or in a dedicated powder diffraction software, in a powder software. Then I showed you how you can do Rietveld analysis, Rietveld refinement in Smartlab Studio 2, or similarly in your preferred powder software. Then I showed you how you can do reference intensity ratio quantification, so another type of quantification. I gave you a brief introduction to PDF, pair distribution function analysis. And I would like to summarize that single crystal diffractometers are maybe more versatile than you might think. So just try it out and collect some powder data on your single crystal instrument. And with that, I would like to thank you very much for your kind attention, and I welcome your question.